Okay, start. Now we will continue with D controller. While dealing with P controller, we said for high value of Kp, there is a possibility that the system, there will be an overshoot, like we will pass the target. If you're starting from A and if the Kp is high, it will pass the target and there will be an overshoot. Because the outcome of P controller is Kp into E of t. So E of t represents the displacement, how far we are from the target. Whereas for a D controller, output U of t is Kd into dE by dt, where dE by dt represents the velocity. That is how fast we are approaching the set point. Velocity is nothing but how fast we are approaching the set point. Suppose if Kp is high, there will be an overshoot, but then if at that instant, when we are approaching the set point, if I relax the constraint and I say that I can apply brakes, then when I am just approaching the target, approaching the set point, if I apply brakes, then I will not overshoot. I may overshoot until this point. So this D action, which depends upon the velocity of error, like how fast we are approaching the set point, this provides the braking action. That is how overshoot is reduced. For low value of Kp, the system response can be something like this. For a critically damped system, the response with P controller will be something like this. For high value of Kp, the response will be something like this. If a derivative controller is introduced, the transient response of the system, the speed of the response remains same because of high P action, but the overshoot will reduce. That is, the transient response is improved. This can be explained with the help of root locus. Consider the same plant whose transfer function is given by 1 by s plus 2 into s plus 4. Now if I introduce a 0, that is PD controller, U of s is equal to k times s plus 8 into E of s, which is in time domain, it is nothing but U of t is equal to k times dE by dt plus 8 times E of t. So this is a PD controller, and this is the new loop transfer function. If we draw the root locus of such a system, these are the open loop poles, this is the open loop 0. So the root locus will look like this. By varying gain k, the roots will travel this path. One will go to the infinity and another one will go to minus 8. So consider this point, if for certain value of gain, the poles will be at minus 3. So its transient response looks like e power minus 3t. It depends upon the real part. And for some high value of k, the pole will be at say minus 10. So the transient response depends upon, once again, real part. So it will look like e power minus 10t. So the farther from the j omega axis, the faster the system is. Faster the system response is. So this can be seen in the output equation, output response of the plant. The system will have faster response, but overshoot will not be there. And the term dE by dt represents the damping. Even in a spring mass damper system, For such a system, this represents the coefficient of dx by dt represents the damping. So dE by dt or D controller improves the transient response of the system. So depending upon the given damping ratio, the value of K can be obtained. From the given specifications, one can easily obtain the damping ratio, and from there they can obtain easily the gain of the PD control. This finishes.